Hey, this is Leach with Simpson Math, and in this video, I'm going to be talking about confidence intervals, specifically just a broad introduction to confidence intervals, making sure that we're good with the main idea of them, how they're structured, and then towards the end, I'll be answering some questions that you might see on maybe a homework assignment. Specifically, it's from the textbook that I'm using in my stats class, Larson, the Larson 8th edition book. So there's some questions from that I'm going to model. The main idea is just what is a confidence interval? So let's get started. So first, just the idea behind stats. If you're at this point in the class, we're finally at this point of the inference. So on the screen here, I want to know what mu is. I want to know the population mean. I don't know what it is. So what do? I take a sample. So I go get a random sample of some size, and from that size I get a sample mean. And so on the screen I have written down that I got a sample mean of 37.67145. So do you think that x bar is mu? Do you think that is the population mean? Do you think that the x bar sample mean equals mu? Now, if you think about it for a second, of course not. Of course that doesn't equal mu, but if we are collecting our data correctly and randomly and without any bias, then it should be close. Now, close is a little bit relative. With close, um, sorry, I heard my dog barking now. So close might differ. So if I'm talking about maybe the 24-hour change in the stock market from a whole bunch of different stocks, then close might be several $100s or thousands of dollars. If close is in my face-to-face class, I have students guess my age towards the end of the semester, and we use data with that. So close could be a few years with that. So close is very relative, and that kind of depends upon our standard deviation. So let me show you where I got this information from. So I've turned on an 84, and I've secret. I've told the calculator what m is. M is what is a placeholder I'm using for mu. So the calculator knows what mu is or what m is. I know what it is, but you don't. And so I said, hey, calculator, suppose this is a sampling distribution, and the standard deviation of the sampling distribution, so that would be sigma sub x bar, the standard deviation of the sampling distribution of sample means is 5. So don't worry about how that math works out, but I'm just telling you that when the population standard deviation divided by square root of n gives us 5. So when I do that, and I'm sampling from a normal distribution, randomly 37.6714 yada yada pops out. So we're calling this x bar, this is our point estimate. It's our best guess. It's our best singular guess. But the thing is, it's probably wrong. Like I said, it's close, but it's probably wrong. So what I want you to do, you the viewer, you the probably student watching this, I want you to think about um, like a potential, like maybe a potential kind of maximum um, or a potential kind of minimum. Think about both of those. What would be a number on the high side and a number on the low side that you would be willing to kind of put your money on? So let's say we're in a room full of people and we all put a dollar on the table, and the person who could give us the smallest interval um, that contained the actual truth, contained the actual mu. So if everyone was, placing your bets for what do you think a number is that would be like just too much? So would 100 be 100 a safe maximum? What about 1,000? What about 50? What about 40? So somewhere like where would you go? Ooh, I would bet it'd be as big as here. Uh, if it's bigger than this number, that's probably too big of a guess. And then what about on the low side? So what about 0? What about negative 1,000? What about 20, 35, 37? What would be a smaller guess? So what we're doing is we're fattening up our point estimate into an interval. So I'm kind of imagining we have a number line here, and 37 is right here, somewhere in that middle, somewhere in there, and then we're going to have some number on the high end and some number on the low end, and you're saying that anywhere between here, let me actually color that blue, anywhere in between here is where I think mu might be. All right, so pause the video, take a guess. Where do you think that mu might be? A low end and a high end. All right, so maybe pause the video and you've done that. Um, Hopefully, if this was a classroom discussion, I would have we would discuss a bunch of different things, but let's take a look at, let's use this number. So uh, I didn't just give you this 5 just for my health. I'm giving it to you because it's useful information. Like I said, if this was the stock market, or also it'll depend on sample size, as we know from studying sampling distributions and sample means. So if this was the stock market, 5 would be shockingly consistent. A $5 kind of spread, or a $5 spread amongst my sample would be shockingly consistent. If I was talking about my ages, the guess of people's guess of my age, 5 would feel like a little bit big. So we want to make sure that we're using this to help inform us. Well, um, if you recall back to the empirical rule tells us that approximately 95% of the distribution of a normally distributed or bell-shaped curve is within 2 standard deviations of the mean. So what I'm going to do with my number line here is I'm going to kind of divide this up. I'm going to jump 5. So if I jump 5, 37 plus 5 would land me at 42. So that's 1 standard deviation. At 42 would be 1 standard deviation higher than the mean. Let's jump another 5, and this would put us at 47. So I think a safe maximum guess using this standard error would be the standard deviation of the sampling distribution would be 47. And I could do the same thing by subtracting 5, uh, and then subtracting 5 again, and I would get at 27. So basically kind of plus or minus 10. So the reason, again, so what's the logic behind this? Why am I doing that? Well, in this case, there's almost kind of a 95%, I'm using this word loosely, chance of properly capturing this mu, because I know that in a normal distribution, which we're told this comes from a normal distribution, we're in a normal distribution, that the middle 95% of the distribution is within 2 standard deviations of the mean. So I kind of have this drawn out here a little bit. Let me switch things because we don't need the calculator at the moment. Um, with this, the idea is that I have we have this 95%. If I go up 1 2 standard deviations, down 1 2 standard deviations, that's 95%. That's from our empirical rule. Now, this is a little bit silly, but in the classroom, I try to find the student that's closest to my height. If our heights are the same, our arm spread should be about the same. And I dub that this student is mu, or maybe p, but the point is they're the truth. We don't know where they are. Now they are standing on the mu. They are the mu. We don't know where they are. But we do know where I am. I am this green guy. I'm X bar. And so the idea behind this is I am our arm spread should be about the same. And notice that mu's arm spread is about 2 standard deviations wide. This wasn't an accident where I drew this. So suppose that his arm span is 2 standard deviations wide, and my arm span is also 2 standard deviations wide because we're about the same height. So notice if I'm standing here, I am within his arm span. If I'm over here, I'm within his arm span. If I'm over here, I'm within his arm span. So if I'm within 2 standard deviations of the mean, I'm within his arm span. But the opposite is also true. If he's within my arms, so if I'm within his arm span, then he is within my arm span. Because the thing is, we don't know where he is, but we know where I am. And so sometimes I could be here, sometimes I could be here, here, here. We don't know where I am. Every now and then I might be, oops, a little bit too high where I don't capture him. Every now and then, oops, I might be a little bit too low where I don't capture him. But 95% of the time, I will be within his arm span and he will be within my arm span. So we don't know where he is, but we do know where I am. So so the idea behind a confidence interval is we're going to take our sample statistic, which is our point estimate, we're going to fatten it up, typically about 2 standard deviations wide, 2 standard errors wide. And then 95% of the time, roughly, we should capture the truth. Let's see this in action with this calculator. So the truth, I'll go ahead and tell you, the truth was 45.6. Okay, so notice that if we take a look at our interval that we had a second ago, we thought it was somewhere between 27 and 47. That works. So 45.6, just barely though. 45.6 is within 27 to 47. Now, um, by chance, I might miss sometimes, right? So let's see how often I'm going to miss. I'm going to do this about 20 times or so is my guess. So I've just copied and pasted this random norm m, which m is 45.6, um, comma 5, which 5 is my standard deviations. And so I'm going to plus or minus 10 and see if I get into 45.7. Let me document that mu is 45.7 now. Sorry, 45.6. We know that now. All right. So I'm going to press enter. I get 38. 38 plus or minus 10 does capture that 45.6. Ooh, 50. Now we're on the high end. If I subtract 10, yep, that's like 40. If I go from, if I'm at 50, just to be clear, if I'm at 50 and I go down 10 to 40, up 10 to 60, notice that right about here is a 45.6. All right, so we have that 50, that was my sample mean, and I go up and down 2 standard errors, we would capture that 45.6. Let's do this several more. That captures, so that's 1, 2, 3, 4 that have captured. 5 captures, 6 captures, 7, just barely. 7 captures. If I subtract 10 from here, I'm at 44, so that captures at 7, 8, 9. Ooh, so right here with this 9, if I do 32 and I add 10, notice how we're a bit low now. So this one, this was my ninth one. This one, a sample mean of 37, oops, 32. 32. If I add 10, I'm at 42. Subtract 10, I'm at 22. So notice that 42 is just a bit low. So my ninth one didn't capture. I'm gonna truck on to 20 and see how often we hit. So 10 hits, 11 hits, 12 hits, 13 hits, 14 hits, 15. Oop, 15 is just a bit too big. Notice if I subtract 10, I'll be at 47. What number is that? 15, I think. 16, yes. 17, yes. 18, yes. 19, yes. And lastly, 20. Oops, that 58. I just said yes blindly. That 58 is also too high. So in this one, I ended up with 17 out of the 20 capturing, and 3 of the 20 didn't capture. Let's do that a whole stinking bunch of times. All right, let me push this button. Let me push this button. And now I push this button. Yeah, okay. So this is, if you're one of my students, you probably should be familiar with the Rossman Chance applet collection, my online stat students. But this is an applet that is more of a teachery applet, not one that y'all will be needing to do. So don't stress your pretty little selves out about this. Okay, so but do follow along because it's this is important. So what I've done is I've basically plugged in what we just did. So I have a population mean. It gets a bit bigger for a second. I have the population mean set at my 45.6. I have a population standard deviation sigma of 20 and a sample size of 16. From if you studied, which you should have at this point, studied the sampling distributions of sample means. If I do 20 divided by square root of 16, that would be 20 divided by 4. That would give me 5. So this gives me a standard error or standard deviation of the sampling distribution of 5. And I'm just going to say, hey, give me just one of these. So when I do it just produced this sample that we see over here. It has a mean of 54.494. This is an S, a sample standard deviation. This mean would be X bar. This standard deviation would be S. And then when we produce the confidence interval, it goes from 44.7 to about 64.3. Now, it's not quite plussing and minusing 10. The reason why is because we don't actually use 2 for 95%. We'll use, and we'll talk about this in a second, 1.96. So if instead of jumping 5 twice, I'm going to jump 5 1.96 times. So it's just a little bit less than 10. So notice if I took 54.5 and added 10, I'd be at 64.5. Just a little bit under that, 64.3. Same thing here. If I subtract it, I should be at 44.5, but I'm a little bit bigger than that at 44.7. So we'll talk about that distinction in a second, but notice that it's colored green because I am barely, but I'm capturing my population mean of 45.6. I'm going to speed this up. I'm going to actually do this 100 times total, and it's going to give me 100 of these intervals to look at once. So earlier we did 20 intervals, and in those 20 intervals, 17 of them captured and 3 of them missed. So here in these 100 intervals, um, we have 3 of them missing and 97 of them capturing. So this one here, it's if you can see that it's red, it went from 24.5 to 44.186. So notice that that's below, completely below the 45.6. This one was above the mean at 47.16 all the way up to 66. Now, these intervals that missed, they didn't do anything wrong. It's just due to dumb luck. So we're sampling from a normal distribution. It happens that we get values up here, but 95% of the intervals, sorry, 95% of the samples that we collect should produce an interval that capture the truth. So far, we've looked at 101 of them, and 98 of them have captured. So right now we're at 97% capture rate. Let's do a whole bunch of these, and I want you to watch this number, and this number should be getting closer and closer to my confidence level of 95%. So let's do that. So again, I was at 97%. This time we are at 95. This one was at 94. This one's at 92. Look at all those reds that we have there. So as I do more and more of these, we're getting this interval. The number of times the intervals are capturing the truth is getting closer and closer to this 95. 95%. So that's what it means to be 95% confident. That if I was to produce a sample, and from that sample take a sample and then produce an interval, 95% of the samples collected would produce an interval that capture the truth. We do have to be careful about the word probability or chance, because once the interval is constructed, it's captured. Once an interval has structured, it either has captured or it hasn't. I'm going to make a little hook 'em horns and make a little put my finger up right here. So if I have this right here and I put this between my fingers, it's like if I just kind of blindly throw my hand forward, I might miss or I might capture. If I just blindly throw my hand forward, what's the probability that I just captured my finger? 100% chance, because I did. What's the probability I just captured my finger? 0% chance because I didn't. Okay, it's like if I flip a coin and it landed heads, it's like, oh, what's the probability that that coin just then that just landed heads, what's the probability that it is a head right now? 100% because it's heads. If I'm about to flip a coin, what's the probability that I will get heads? That's 50%. If I'm about to collect a sample and then produce a confidence interval, what's the probability that that sample will lead me to a confidence interval that captures the truth? That is a probability that I can speak about. That I can say I have a 95% probability of capturing the truth when I take that future sample and produce that future interval. That's all I'm going to say about that. But so that's where we avoid probability. So we talk about what does it mean to be 95% confident? That notice that 95% of samples would lead to an interval that would capture the truth. So what does it mean to maybe be, so this confidence is cool, that's 95%, but why not just be really confident? So let's be like 99% confident. I want you to watch what's happening, what will happen to these. I'm going to make this be 99% confident. And you might have noticed, if you look at these intervals, they're wider. Let me do that again. Let me drop down to a 90% confidence interval. You should notice that they are skinnier. Maybe only be 80% confident. Even teeny tiny. 99.9% confident. Look how big those are. So if I don't change anything, but I just change my confidence level, the confidence level is basically like a little bit of a dial, like a dial on your radio, on your car radio, that's controlling the volume. But in this case, it's controlling how confident we are, which then, if I don't change anything else, changes the width. Little story. So I have a gift. You hit a certain age, thankfully past it, that it seems like all of your friends are having babies. I'm childless. Uh, Thank God. But I have this gift that I was able to predict all my friends' babies' birth rates. One of my friends, their most recent births was twins, so that kind of made it be a little bit trickier. But I was able to kind of, with their permission, kind of hovered my hands around their belly, and I was like, and I predicted that my friends' twins' birth weight was gonna be somewhere between like, as twins was a little bit tricky, somewhere between like 0.2 pounds and 25 pounds. It's great because I've never been wrong, so I'm really, really good at this. So let me say that again. I predicted that my friend's birth weight, who's going to give birth to twins, their birth weight of those twins was going to be somewhere between zero point 0.2 pounds and 25 pounds each. If you're paying attention to this, you're probably like, oh, good grief, that was like, okay, Leech, that's a really big interval. That's not very helpful. Exactly, but I was very confident. I could be very confident because it just produced a really, really, really wide interval. Confident, but not very useful. So we want to have intervals that are narrow, but notice I can increase my confidence by just making the interval wider. But that's not really helping the matter too much often. So the just behind this, if I increase my confidence level and change nothing else, I'm gonna have a wider confidence interval. If I decrease my confidence, then I'm gonna have a narrower confidence. Sorry, narrower interval. All right. I'm just going to show you this real fast. I'm going to switch applets over to this one is with proportions. So I looked up stats for Temple College, and according from the U.S. Department of Education, we had 70% students are female of our about 3,000 students. So I said, well, if that's the truth, that's 0.7, 70% of our students are females. Let's say I take a random sample of 45 students, and let's see. Now, this is a weird thing because when you're doing confidence intervals, I wouldn't do a confidence interval for something I know the truth of. Let's say you didn't have access to that data. So we're kind of simulating things that we know. We know it's 70%, but maybe in that moment, or maybe when we see evidence that it's changed, because that was back in like 2021. So, but if I take this one sample, this one was a real low, but it went from 41% to 70%. So I sampled 45 students, 55.6% of them said that they were female. So if I was to produce an interval, because I don't know the truth, that it would be that I was estimating that somewhere between 41 and almost just over 70% of students would be females. So let me do that a whole bunch of times again. And when I do, so notice here I get several that miss. I have like 6 that miss. Here I have like 4 that miss. So the same thing happens. So what does it mean to be 95% confident? It means to be 95% confident that 95% of samples that we would produce, that we would collect, would produce an interval that captures the truth. So sometimes like this one we get really unlucky and got a really high proportion of females, so we missed. But more often than not, we're capturing the truth. By more often than not, 95% of the time we're capturing the truth. And again, I could do the similar things. I could increase my sample size to 99. I'm going to actually sort this because you'll see it better. If I recalculate this to 99, you'll see how that gets wider. Let me change this to 90. You'll see that it gets skinnier. If I want to be maybe 80% confidence, even skinnier. Something crazy like 50%, it's really tiny. See how much we're missing? We're missing about 50% of the time here. Again, we go back to 99. So they can get really wide, 99.9. So we see how what it means to be confident and how adjusting our level of confidence adjusts the width of this. All right. So I think that's good with that. Let's talk about the structure of our confidence intervals. So with our confidence intervals, um, we typically write our confidence intervals with a point estimate plus or minus some margin of error. I often abbreviate margin of error as just ME while I'm doing a little bit of math for margin of error. So it's Our point estimate, this point estimate is our statistic. It could be an X bar or p hat, or our two most common things. Later, we'll see how it could even be the difference of a p hat, p hat 1 minus p hat 2, or X bar 1 minus X bar 2, two different means or two different proportions. So some sort of sample statistic. So that is our best guess, our best estimate. If I'm trying to estimate a population mean, I'm going to be using X bar. If I'll be wanting to estimate the population parameter p, I'll use p hat for my statistic. All right, and then our margin of error. So we did this innately a second ago. We said, well, we're just going to take 2 times our standard deviation that we got earlier, and we multiply that out. Now, I have done a little bit of a vocabulary swap here. Instead of a standard deviation, I'm going to call it a standard error. So a few reasons for that. One is mainly in our coming up sections, we're not going to be using population parameters. Instead, we're going to be using like S, or the formula for with the proportions uses p hats. So it's kind of our best guess of the population standard the standard deviation of the sampling distribution. And so that's where we're going to be referring to as a standard error. But right now, from like our last section, we saw sigma over square root of n. Ooh, let me uh, make this note. If you're in my online stat class, I do not really heavily teach finding confidence intervals with a known sigma. The dude in the video from my lab, or the book, will talk about it. Any of the problems from this section does not use sigma, or if it does, the problem gives you the confidence interval. So I don't make a big deal about it because it's not very practical, but it is what we have right now to teach with. Um, so this critical value, this is, like I said, this is the knob, this is the dial that controls how confident we are. The bigger knob this is, the more confident that we are, because it's the greater number of standard errors that we're multiplying out. Our Larson book, uses Z sub C. That's, in my opinion, not as standard as using Z star, Z with this like kind of floating asterisk. But either of these will work. So this is C for like our confidence level, and stars is just saying it's a special Z. So our example that we saw at the top of the video, it's our sample mean plus or minus 2 times our standard error. Our sample mean was this 37.67, and we plus or minus our 2 times our standard error, and our standard error was 5. So 2 times 5 is 10. And there's two ways that we could write our confidence intervals. So we can write a confidence interval as with our stat plus or minus the margin of error. So this number collectively is the margin of error, because I'm going to take my stat and add 10 and then subtract 10. Or we can write it with the upper and lower bounds. So my lower bound and my upper bound. This is technically an interval notation, so we're using parentheses. So if you think back to your algebra days, if you had any, even like algebra in high school, you talked about interval notations. So it's not square brackets, because square brackets implies they were touching that value, but we are approximating that, so the ends are a little bit fuzzy, so we visualize that with these parentheses. All right, so let's talk about finding that 2. So here I used 2. That's cool, because that's from our 95% knowing 95% rule, or the empirical rule. But let's actually find out what it is, because it's not just going to be 2 anymore for 95%. That was always an approximation. So just to be clear, C in this chapter, we're going to be lowercase c. We refer to that as our confidence level. So if C is 0.95, then that means I'm 95% confident. If C is 0.9, I'm 90% confident. I'm less confident, so I should have a smaller interval. So where can I get this? So it should be 2, and it's going to round to 2, but we're going to get a little bit more accurate. So I'm going to pull up our there we go. I'm going to pop on over to our normal probability calculator. So the another Rossmann chance applet, make it be a scoosh bit bigger. There we go. I could change this to these because I'm just dealing with z's, but it doesn't really matter. So I'm just going to leave it at that x. But since I'm dealing with these, I'm going to leave my mean and standard deviation at 1, because this is the standard normal distribution. And then I need to deal with these boxes here, but I'm going to go back to my picture because I need to process what's going on here. I need to know what to put in. So if I'm being 95% confident, so this is the same thing as doing that middle 95%. So if the middle 95% here, so if right here in smack dab in the middle is this 95%, then what is on the ends here? Well, um, I I like to do um, when I do this, I teach this in class. It's what I call the middle percent dance. So I kind of imagine that there is a normal curve right in front of my face. And I say, okay, well, everything right here is 95%. So if everything right here is 95%, actually, rewind. I forgot one part. All right. So we have a normal curve right in front of our face. Everything under the normal curve is 100%. Right here in the middle is 95%. I'm going to subtract that. So total on the wings and these little edges over here, total on these edges, we now have 100 minus 5, sorry, 100 minus 95 or 5%. So just one of them is 2.5%. So let's do that again. So we have a normal curve in front of our face. Everything under this normal curve is 100%. Here in the middle is 95%. Delete it. Total we have now, total on the edges is 5%, and each is 2.5%. We have that. So I'm going to make that note to myself that on this end is 2.5%, and in this end is 2.5%. And I can always add those up. 2.5 plus 95 plus 2.5 does give me 100. Or specifically, we could do well, the 100% minus 95% over 2 is where that comes from. So, with that said, let's take a look at this Chrome situation. Sorry, I went to Google Chrome. Let's look at our Ross-Chance applet for the normal probability calculator. I like to make one be less than, one be greater than. Habit makes me have the second one be greater than. And in my probabilities, I'm going to put in those tail probabilities. So 0.025 on both, 0.025 on both. And so if I'm at a z of negative 9.6, I can't read today, negative 1.96, that's this line right here, just a skosh off of 2. The area less than that is 2.5%. On the upper side, a positive 1.96, that's this line up here. The area to the right of that, greater than that, is 2.5%. And look what's in the middle, the probability between those, 95%. So especially in this middle percent game, when you put in the numbers, double check that the probability between your numbers is the number you're looking for. And again, x and z are the same because we have our mean and standard deviation set to the standard normal distribution, mean of 0, standard deviation of 1. So the z's that we would use here, the z's that are separating the middle 95% is negative 1.96 to positive 1.96. But Z star is really just, let me swap my colors. Z star is just this positive 1.96. So see how this left one is written? Negative Z star or negative ZC is a negative 1.96. So a positive Z star, positive ZC is 1.96. I don't know what MyLab is going to be wanting to use. Maybe actually I do. I could look right here. 2 decimal places on one of the examples. So round accordingly. So just to be clear, if the answer to this question, and we'll see this in a second. So I'm just looking for what is ZC or Z star, and that's at 1.96. We don't deal with the negative. It is inherent that it's the negative at the symmetric location away. All right, so I'm going to do 90, 99, and 80. If you want to pause the video and try it on your own, cool. But I'm just going to go ahead and truck ahead. So I'm going to do, I need to find out what is basically my Z star. So that way if I have a Z star or ZC and a negative Z star or negative ZC, that will give me that middle 90%. So let's swap it. So let's change this. Oops, let me go back to my picture. Silly me. So if this is 90%, if everything under the current normal curve is 100%, here is 90, make that go away. 90 minus 100 minus 90 is 10%, so I have 10% total in the wings. Each of them is just going to be 5. So I have a 5% here or a 5% here. Do be careful about writing 5%. As a decimal, that is 0.05. 0.05. If you wrote 0.5, That's 1/2 or 50%, which is not what we're looking for right now. All right, so now let's go to our applet. 1 less than, 1 greater than. Let's change our tails to be 0.05 on each. And the z's should become the same value, just with different signs. So 1.645, positive, negative, and area between is that 0.9. So I get 1 point, oops, wrong color. We get 1.645. There's a bit of a to do with, like, if you look this up in the table, it is closer to, say, the 1.645. So that's the more common thing. It's usually have that 0.45, that extra 5 on there for the 90%. All right, 99%. So again, if you do the middle percent dance, you have 100 minus 99% is 1%, so 1% total in each, sorry, total between each, and so in each of them would be a 0.5%. So oops, I wrote that wrong. No, I wrote that right. This would be it would be 0.5%. Yep. So 0.5%, like so. So just to be clear, as a decimal, 1/2 of 1% is 0.005. That's 1 out of 200. And if you're, remember, I don't know if you're, I don't know if in a video I've said this, but anytime my brain breaks and I'm like, ugh, percents and decimals, I write this down. 1/4 equals 25%, which equals 0.25, something like that. And doesn't matter the order. I'm confident that everyone taking this stat class should know this information cold. That should have a permanent residence in your brain. That reality. So that way, if I know that if have a decimal and I want to turn to percent, I'm going to go 2 to the right, move the decimal 2 to the right, or if I have a percent, I need to go to the decimal, it's going to go 2 to the left. So if I have the decimal, I want to go to the percent, we go 2 to the right, 0.5, or if I have the percent, I need to go to the decimal, 2 to the left, 0.005. All right, so now what is the z-star for this? So same thing, I've lost my mouse, there we go, 0.005, 0.005, I can just be cheeky and add a 0. 99 in the middle, and I get 2.576. So right here, this Z's 2.576. So Z star, or Z sub C, is 2.576. The 95%, 90%, and 99% are 3 of the most common or popular Z's or confidence levels. So those you should almost know cold, put on your note page, things like that. Something you can easily reference to. 80, less so much, and then our example we'll see in a second is a obscure one that's just making sure you know the mechanics of it. All right, so what are these percentages? If everything is 100, 100 minus 80 is 20. Cut that in half, and we have 10% or 0.1 in each of these. 10% or 0.1. So let's go to our applet, put 0.1 in each of those, double check that we have 80% in the middle, 80% in the middle right here. So we're at 1.282. So Z star is 1.282. All right, so knowing those, especially these 3, can really help you make sure that, that your answers are making sense when you see something like this. So I'm going to be working through some examples that you'll see if you're in my online class, that you'll see some examples in these on the homeworks. So let's find the critical value, Z sub C, necessary to form a confidence interval at the level of confidence shown below. And it wants a level of confidence of 0.89. So what I like to do is like to draw a picture. So I know that if it was at 2, that would be 95%, and that's a little bit extreme. 80 was at like 1.2, 90 was 1.645, so this should be somewhere between about 1.5-ish or so, just to kind of be able to eyeball it. And I'm just going to say that this is my 0.89 or 89%. And I want to know, I have this ZC and this negative ZC, so what is the value of ZC? All right, So let's go over to our, oh, sorry, before then, I need to fill in what is this. It's a little bit weirder, so I'm going to do 100 minus 89 and then half it. So that's 11 halved, or 5.5%. So as a decimal, that's 0.055. Yeah, 0.055 on both ends. All right, so I'm going to come over here and put in 0.055 in both. And a nice way to check is to check your probability between. This probability between better match up to my 89%, and it does. So that makes me feel good about the numbers I put in here. So to 3 decimal places is 1.598. This would be a ZC of 1.598. But the almighty blue words, I think, say something different. Almighty blue words say they want 2 decimal places. So 1.598 rounds to 1.6. All right. This one. Use the values on the number line to find the sampling error. So sampling error is error that happens when you sample from a population. You take a sample, and what type of error happened in that sampling process? Well, mu is what I was expecting. This is the truth. That's my mu, in case you can't see that. And this is my x bar. So all throughout this course, you should, especially when you were learning about standard deviation and things like that, when you're learning about z-scores, we're seeing how we had the difference in what we were observing minus what we're expecting. So I kind of abbreviate that obs minus or observed minus expected, or just in general, O minus E, what I'm observing minus what I'm expecting. So in this case, what am I observing? I'm observing X bar. That's what I observed. That's what was tangible to me. Minus, what was I expecting? Well, I was expecting that if I sample from a population of mu, I should get mu or something close to it. And this is then something close to it. I'm a bit off from it. Notice this idea, observe as expected, we see in z-scores. So this is not something new. When you do x minus mu over sigma, this is what I observed minus what I expected. This numerator is just a deviation. That deviation is what we see when we do the standard deviation formula. So these are basically versions of a deviation. And at the end of the day, guys, this is what stats is about. This is what I observed. This is what I expected. They're not the same. Is that weird? So if you follow that process, this observed as expected, notice we did get a negative number because when I do 3.2 minus 3.47, I do get a negative 0.27. And that negative doesn't make sense because isn't my value lower, below, less than, to the left of what I was expecting? So this is the point of view. That's what's nice about this formula, observe as expected. What I'm expecting is my point of view, and this thing was a little bit below it. That's why it's negative. So that logic kind of makes sense, that I'm lower than what I was expecting. If you got a positive number, that's because we ended up to the right of what we were expecting. So it's not always negative. If it's negative, that means it's less than it. If my x bar was like up here, then I would expect a positive sampling error. Obviously, our sampling error we want to be as small as possible, but this happens due to random chance. All right. This says, for each level of confidence, see below, determine the corresponding normal confidence interval. Assume each confidence interval is constructed for the same sample statistics. That's important. So the same X bar, same sample size, all that. So notice the only thing that's different between these. So notice they all have an X bar of 56.1. These ones over here too. They all have an X bar of 56.1. But some of them are skinnier and some of them are wider. This is an example that's on the homework. And with this homework, I left you a note, if you're my student in my online class, that says this problem is dumbly put together. It's a matching question, but they have it be a multiple choice question, and the multiple choices keep scrambling. I don't understand why they did that. I want to write ugly letters to Pearson sometimes. But nonetheless, we're able to match this. So basically, guys, take a look at our values. Let me sort my confidence levels that they give me in order from least to greatest. So the smallest one that I see, let me just write them down here. So the smallest one that I see is a 0.85. The next one, oh, they are in order. How about that? Well, I'll just go ahead and do this. 0.9, 0.95, and then 0.98. How nice of them that they're already in order. And so what I saw earlier, that the larger my confidence, if I'm changed nothing, if my stats don't change at all, I just am more confident, then something has to give, and that's going to give in the way of a larger confidence interval. Also, take a look at these numbers that we saw here. Um, my larger confidence levels uh, my larger confidence levels had a larger z's. My smaller confidence levels had a smaller z. That's what, you know what that is not? That is not a coincidence. That's because, remember, this critical value is the dial with which we control the width of our confidence interval, because this margin of error is the width. This number is in the center, and this is how wide the interval is. So I'm going to plus or minus from that. Well, how much am I going to multiply by my standard error? Well, if I'm 99% confident, over 2.5. If I'm only 80% confident, only like 1.3. Our default value is at 95% at about that 2. So basically, looking at my intervals, which is the skinniest interval? Well, I see between these two, this one's skinnier. And then between these two, this one's skinnier. So if I just compare those two, I say this one is 54.2. This one's a little bit skinnier inside of this. And same thing, this one's 58. That's a little bit larger than this. So my skinniest interval is this one up here. So I'm going to put the 85 on that one. And then so the next skinniest would be the 0.9. Um, there's not much change between 90 and 85. So if we were to do the 85, let me actually swap it and look at it. 85 would be 7.5, I believe. 7.5 on either end. Yep, 85. So notice this is Z star or ZC of 1.44 compared to 1.645. So that's not much of a change. That's barely any change. There's a little bit more of a difference between the 95 and the 98. Um, sorry, between the 95 and the 90, I misspoke. So I need the next biggest one. Um, so this jumps up to 53.4 versus 53.8. So this one is just a little bit more narrow than this one right here. Is that right? No, this one is wider. Misspoke. This one is wider than this one right here. Because this 53.4 is beyond, it would be like here. 58.8 would be like here. So this one is the next skinniest. Oops, didn't mean to move that one. This one's the next skinniest, and this one is the biggest. So it's all about matching. The way that the homework is delivered a little bit on that is a bit annoying, but that's all that is. Is that the smaller the confidence level, the smaller the interval, the skinnier the interval. The larger the confidence interval, the larger the interval. And again, it has this caveat if all the sample stats are the same. All right, the last thing that we'll cover is this question, and I'm going to actually cover these other questions first. Um, no, I'll do this one first, and then I'll just show you some extra practice. So, um, we're going to use a confidence interval. So I'm giving you a confidence interval, a lower bound, upper bound, and basically we're turning it into this other version of what plus or minus what is this confidence interval. So what's the other form of the confidence interval is kind of what it's asking. So we need to know the margin of error, which is our margin of error over here, and the sample mean, which is our stat or the X bar. So what I'm going to do is I'm going to draw a number line just to help us visualize this. So I have some number in the middle. That's going to be my X bar. I meant to actually not have these colors. Let's do green for my X bar. And my margin of error is going to be this blue. So if I have an X bar, and then I plus or minus the same amount, those little jumps should be the same, plus some margin of error minus a margin of error. That's going to land me at the numbers that they provided, 2.02 and 1.72. So we should notice something, that our intervals are two margin of errors wide. Don't confuse that 2 with z star. Okay, z star is how wide our margin of error is. So the z star is how many standard errors wide one margin of error is. The entire interval is 2 margin of errors wide. So there's two ways we can go about doing this. We can either average these two numbers to get the number in the middle, or we could find the distance from here to here, and cut it in half. Either method kind of works. I like finding, I'll show you both ways. I'm going to take these two numbers, add them up, and average them to be able to find this x here, x bar rather. So if I take 2.02, add them up to 1.72, 473, and if I divide that by 2, I'm going to grab a calculator. 3.74 divided by 2, and I get 1.8. Let me write that down. That'd then do 2 divided, 3.74 divided by 2, and I get 1.87. So visually, does it make sense that if I average these two numbers, because this number is smack dab in the middle, so if you find the midpoint of two numbers by adding them up, dividing by 2, I'm going to get that number in the middle. So that's where I get this 1.87 from. Okay. Now that I have that, there's two ways that I could get the margin of error. To get the margin of error, I can do 2.02 minus 1.87. Basically, it's the distance from here to here. Let me write this down. This is the 1.87. Now, on this question, I think on a quiz, I don't know if they both show up. Or I think on the homework, it might ask for the margin of error first. I think on the quiz, they both show up. But obviously, you see how I found the standard error first. Sorry, I misspoke. I found the sample mean first. Just find the sample mean first. But I'll also show you the other method as well. So if I do this subtraction, it'll give me this distance between here and here. You can do this. You can use the formula, or you can just use a calculator. I mean, you can do it by hand or use a calculator. 2.02 minus 1.87, and I get 0.1. Oops, I mistyped this number. That's why. 2.02 minus 1.87, and I get 0.15, which is what I was expecting. I could double check that I could also do 1.87 minus 1.72, and when I do, I will also get 0.15. All right, so that's how you can go about getting the x bar first, and then how to find the margin of error, or how could we go about finding the margin of error first? Well, if I just find my total distance between here and here, because remember I said it's 2 standard errors wide. So if I just do 2.02 minus 1.72, and I subtract that, I should get 0.3. So this one is 0.3 units wide. The entire interval from the lower boundary to the upper boundary is 0.3 units wide. So for my margin of error, if I do that 0.3, if I do my 0.3 divided by 2, notice how this is a faster way to be able to get directly to the margin of error, which is that 0.15. Now that I have the 0.15, how do I get my 1.87? Well, then I could just take my my lowest number, 1.72, and add 0.15 to it. 781. There's my 1.87. So either method works. So the idea is you can use the fact that this interval is 2 margin of errors wide, find that total distance, and then cut it in half. There's your margin of error. Add your margin of error from the bottom or subtract it from the top to get your number in the middle. Or what I did at first was to find your mean, you take these two, you cut them, you find the average of these two numbers, which gives you the midpoint, and then just subtract it. Subtract the upper boundary from the middle, from the mean, or the mean from the lower boundary. So that's how you do that. All right, I have several questions that I'm going to go a lot faster, um, and there's a bit of redundancy here. So I'm going to give you a description of a confidence interval in some form. Basically, it's in one of these forms, and you want to be able to find all the others. So what's the point estimate or the sample stat? What's the number in the middle? What's the margin of error? What's the lower boundary? What's the upper boundary? And then to be able to write it in both forms, our stat plus or minus our margin of error, and then our lower bound, comma, the upper bound. So if I look at this, 50 plus or minus 10. So just to be clear, this 50 is my stat. So this is the 50 is my estimate or my stat. And this 10 is the margin of error. All right. Um, so then how do I convert from this to my interval? Well, let's just add. Add and subtract. So if I do 50 minus the 10, that's going to give me my lower interval. And if I do 50 plus the 10, that's going to give me my upper interval. My upper boundary. So 50 minus 10 is 40. 50 plus 10 is 60. So my lower boundary is 40, upper boundary is 60, and the other way to write it is in with those parentheses. So this one here is like the question we just had. I'm giving you the boundaries, and from that you need to know, you need to be able to figure everything else out. So 80 is my lower boundary, 120 is my upper boundary. I'm not going to write it down. Now basically I need to find what is my margin, what's my stat, what's my margin of error. Well, with these numbers, it's a little bit faster for me just to find that if I add them up, I get 200. 200 divided by 2 is 100. So I know that the number smack dab in the middle of this is 100. Or I can kind of have a number line here, 80, 100, 120. So my stat, the stat or the estimate is that 100. And then if what's the distance between 100 and 20? Is that 20. So the other way to do this confidence interval is my stat or my estimate, which is 100, plus or minus my margin of error, which is 20. Of course, you can do the other way around. I see that this total distance right here is 40. And then if I half that 40, I get 20. And so there's that 20. And then I can do 20 plus the 80 to get to the 100. All right, so this one, I'm going to kind of just mark this with a number line here. So again, so if I have a number here in the middle, there's my upper bound, put parentheses here, a lower bound here, let's put parentheses here. So what do I know? I know that my my point estimate is 20, my lower boundary is 15. So what can I see from this? Well, I see that the distance from here to here is 5. Well, that's my margin of error. My margin of error is 5. So if I do another 5, then that should put me up at 25 for my upper bound. So two ways of writing my interval: 20 plus or minus 5, the estimate plus or minus the margin of error, and then, or my lower bound, 15 to 25. How about that? All right, this one's similar. I'm going to do that same thing. I'm going to just copy this as a little template. Oops, I grabbed the text. I don't want the text. 1 second. Copy, paste. All right, so what do I know? I know that my point estimate is a negative 50, and my upper boundary is a negative 30. So let's be careful about negative numbers. Negative 30 is bigger than negative 50. What is the distance from here to there? Do we say that that's 20 units wide, 20 units far? Again, margin of errors are always going to be positive, or you can think of them as they inherently have a positive and negative attribute on it, but that plus or minus is already there. So I could subtract a 20 to go down further. So if I've lost $50 and then I lose $50 more, then I'll be at a negative 70. And I can check that by adding 20 to negative 70, adding another 20. So now with all that, I can summarize this to be it's a negative 50 plus or minus 20, or from negative 70 to negative 30. And again, this negative 70 is smaller than this negative 30, so that's why it's written first. Always do intervals low to high. Oh, I didn't make a big deal of that earlier, but gotta make sure that it is low to high, small to big. If someone asked you, if you had like a face-to-face stats class and they said, when are you taking stats? You're like, oh, from like 12:40 to 11, Monday through Thursday. They'd be like, what? You're there for like 12 hours? Oh, no, no, no. I mean 11 to 12:40. We like to say in the intervals the smaller number first, so small to big. Right. Um, use my little graph. My lower boundary is 5. My upper boundary is 10. So that might be helpful to kind of visualize this. So there's a few ways you can go about doing this. We could see that total this distance here, if I want 2 of those, but that total distance is 5 units. So each of those would be 2.5. So then if I do 5 plus 2.5, that's how I get this 7.5. So my margin of error is my confidence interval is 2 margin of errors wide. I see that it takes 5 units to go from the 5 to the 10. So half that distance would be 2.5. Or you could do 5 plus 10 and get 15, half that to get the 7.5, and then do some subtraction. All right, if my margin of error is 50, so from here to there is 50, from here to there is 50, and my point estimate is 10. Well, they just gave us our 10 plus or minus 50. They just gave us that version. Now we just need to do arithmetic. Let's do the subtraction first. 10 minus 50 is be careful. 10, if I say, oh, here's $10. Oop, now you owe them $50. You just lost, you had a net gain, or actually net loss of 40. And then if you had 10 and you gained 50, you'd be at 60. Notice that is 100 units wide. Might not look like it because the way that goes over that negative. Right? What about this one? So if my margin of error is 12, and my lower boundary is 36, then I just need the middle and the upper boundary. Let's just add 12. So if I add 12, that's where we get 48. Add another 12, and we'd be at 60. So it's 48 plus or minus 12, or 36 to 60. I think this is the last one. So if my margin of error is 10, and my upper boundary is a negative 100, do be careful because we're in the negatives. If you're standing on negative 100, let's say you've lost $100, you borrowed $100 from somebody, and then you just lost 10 more dollars, you now owe them $110, right? So that's negative 110. Subtract another 10, and that's a negative 120. So here you can be at a negative 110 plus or minus 10, or the interval from negative 120 to negative 100. All right, I hope that helped seeing all those different little ways, especially in this kind of visualization of it. This question kind of throws some students, so seeing it visually on a number line should be helpful. All right, so just over an hour, but that's also my typical lecture that I give on 6.1 anyway. So I hope this helped you understand the big picture of confidence intervals a little bit more. If not, ask me some questions or check out another video. I'll see you in the next one. Bye.